All right, so in this particular video, we're going to be looking at logistic regression from the point of view of only computation. So I will say that there are lots and lots of things within logistic regression that are very interesting from a modeling perspective. Just like linear regression, it can be a whole course in itself. Logistic regression can take vast number of lectures really to understand. But we are only focusing on the computational issues associated with logistic regression only. And so it's going to be a rather quick understanding. But the reason we're looking at logistic regression is because it's a great example of a multivariate Newton-Raphson implementation. So let's get started. So we had the sort of setup of linear regression when we were modeling a continuous response. What I mean by that is that our y was a continuous random variable, and so the thing we were measuring or the thing we were interested in was continuous. But when y is a response that is made of ones and zeros, so that means it's a binary response. Now, y being ones and zero doesn't mean it has to always be one and zero. Y can be yes and no, and then you can map yes to one and no to zero. Y can be high and low, and then you can map high to zero and low to one, or vice versa, right? So what we're looking at is basically binary responses, and then you can code either of those two binary responses as ones or zeros. Okay. So, but if the idea is that if we have binary responses, Bernoulli responses, then assuming that the y's are normally distributed, like we did in our linear regression model, where we said that yi is equal to xi transpose beta plus epsilon I. Well, this no longer is a reasonable idea when epsilon i's are normally distributed, because then we are assuming that our y's over here are continuous, and we can't really assume that because y's only take the value 0 and 1. So instead, what do we do? So a popular thing to do instead is to say, well, what we've done is we have a massive amount of data or information about the ith observation. So if I look at the ith observation, I have covariates or information about the ith observation. So for example, what we could be measuring would in the y's could be, for example, whether you're going to pass or fail an exam. So your y's are 1 or 0, 1 for pass and 0 for fail. Now the amount of information you have could be p different characteristics about you. One could be, for example, how many hours of effort have you put in? Another information, xi2, and I being you, 2 being the second covariate, could be, for example, how many hours you sleep. Xi3 can be, let's say, your IQ level. Xi4 can be how much marks did you get in the previous exam, and so on, right? So you have these sort of information about you that can help us understand whether you're going to pass or fail the exam. Question is, how do we use that information in the model? Well, yi over here is whether you pass or fail in my example. Now the question is, with what probability am I going to pass or fail? So I'm assuming then that any ith person passes or fails. So passes with probability e to the power xi transpose beta divided by 1 plus e to the power xi transpose beta. It's a weird looking function, but I'm going to assume that the probability of passing is pi. Okay. Which means that I can essentially say the following, that yi's are all independent of each other, and each individual's probability of success is dependent on their individual characteristic vector xi through this parameter beta that is not known to us. Okay, so I'll repeat that again, that the probability of success or whether yi is going to be pass or fail is critically dependent on the individual's information vector xi via this ratio, which involves this unknown number beta, which tells us basically how important each of these xi's is towards understanding yi. So our whole goal is now to understand and estimate beta, the maximum likelihood estimate. Okay, so this is our code. Hopefully that makes sense. Now, of course, like I said, that there's why exactly this choice of the ratio? Does it make sense for this to be Bernoulli? It probably makes sense for yi's to be Bernoulli since only two observations are possible. But why this ratio? Why not some other ratio? We could take some other ratio as well. In fact, there are other ratios possible, which leads us to, probit regression. It also leads us to, let's say, quotient regression. It leads us to robit regression, and so on. Okay, so the different other functions over here can lead us to different types of regressions, but the most popular one is in fact the logistic regression function, which is this function, right? So for the purposes of this video, this course, we're going to keep our attention restricted to this. But now the idea is the following, that what's given to me are observed yi's and our characteristics on each individual xi. Okay, having observed this data, can I guess beta? Right. So that's the question. Having observed these yi's and xi's, can I guess beta? And yes, we can. We can, using this setup, this Bernoulli likelihood setup, we can actually set up a likelihood function because we know yi completely in terms of its likelihood. Okay, so this is what we're going to do. We're going to estimate beta using maximum likelihood estimation. So as usual, first we write down the log likelihood. But to actually write down the log likelihood, we write down the likelihood function. Now, likelihood function of beta given y is nothing but the product of I going from 1 to n probability that capital Yi equals Yi, because that's my data, right? So the likelihood function is nothing but the joint distribution of all the observations, and in which case, in here, the joint distribution is the joint probability mass function. Okay. Now, probability yi equals small yi, well, that I know this thing, since yi is distributed according to Bernoulli pi, I know that this probability that capital Yi takes a value small yi is actually pi to the power yi, 1 minus pi to the power 1 minus yi. What we have to keep in mind is that the probabilities of success are pi and not p. So every individual I has a different probability of success, and we need to keep that in mind. So now I have product I going from 1 to n, pi to the power 1 I, 1 minus pi to the power 1 minus 1 I. Okay. At which point I take the log of this likelihood, and taking the log makes life easier. Now notice I'm not going to substitute what pi is just yet. Even though I know pi takes this ratio, I'm going to wait. So this now becomes summation I going from 1 to n, yi log pi when I take the log, plus summation I going from 1 to n, 1 minus yi log 1 minus pi. Okay. Now, I have this expression here, and I have this thing that comes and multiplies with the 1 over here. So this just gives me summation log of 1 minus pi. And then yi is common in these two expressions. So I bring yi outside, and I just get log pi minus log 1 minus pi. Okay? Okay, but now let's actually do some math. So pi is equal to e to the power xi transpose beta 1 plus e to the power xi transpose beta. This is what pi is. Okay, so I'm going to zoom in here. So this implies 1 minus pi is equal to 1 minus e to the power xi transpose beta 1 plus e to the power e to the power xi transpose beta, which I know is equal to 1 plus e to the power xi transpose beta 1. Okay. Which then implies that if I take log of 1 minus pi, then this is just going to be equal to minus log of 1 plus e to the power xi transpose beta. Right? And that is exactly what I'm using over here. Okay? So I take this expression log of 1 minus pi, and I and I replace it with this expression here. Okay, great. Hopefully that makes sense. Now let's pivot to the other expression over here. Now, pi, like I said, is e to the power xi transpose beta divided by 1 plus e to the power xi transpose beta. So what is log of pi? Log of pi is log of e to the power xi transpose beta minus log of 1 plus e to the power xi transpose beta. And 1 minus pi I just found out. So I can write log of 1 minus pi, which I just found out was nothing but minus log of 1 plus e to the power xi transpose beta. Which implies then that log of pi minus log of 1 minus pi is nothing but the differences of these two. So this gets cancelled and I just get this expression log of e to the power xi transpose beta. But that is nothing but just xi transpose beta, right? Because it's log is to the base e. Right? And that's exactly what I substitute over here. So this thing over here just matches this thing, right? Of course, there's a yi because there's a yi present over here on the outside. So that means I now have a nice reduced form that log of the likelihood takes this expression over here, and this is a fairly reduced expression. Okay, I have my log likelihood set up, and now I want to maximize this log likelihood. Now let's take a second to understand that beta is p-dimensional, right? So beta is defined in p dimensions, which means if I want to maximize this, I have a p-dimensional grid on which there exists some beta star which maximizes this function. I want to find that beta star which will correspond to my MLE. The challenge is that this particular function need not have an analytical maxima. And that's what we're going to find in order to find whether I have an analytical maxima is I will take its derivative, which is going to be a gradient vector, and I'm going to set it to 0 and try and see if a solution is possible. That means taking the derivative is the first step. So in order to understand how we take a derivative, we can do it two ways. We can do it element-wise, which basically takes this partial derivative expression over here, where you take an objective function and then you take a derivative with respect to theta 1, theta 2 up to theta p. And that's what we're going to do first. But then another way to try and get used to this idea of taking derivatives with respect to a vector would be to do it in one go. And that's just something to get used to as well. But let's take the derivative. So this is our expression of the log likelihood. This is what we found. And I'm going to solve it a little bit. So I look at this. Now, if I look at this expression, I can solve it a little bit because remember, xi is a vector, beta is a vector. So xi transpose beta is nothing but this xi transpose beta vector, which is then nothing but summation xij beta j going from 1 to p, because I'm taking one element and multiplying here and then adding it, right? And adding them all. So I can rewrite that over here like this, where I get yi xij beta j, I going from 1 to n, j going from 1 to p, okay? Minus summation I going from 1 to n, and the same expression here, except again I can open xi transpose, right? And I get j, where this is inherently going from 1 to p. Now the reason I've done this is because in the next step, I'm going to take the partial derivative with respect to an s. So what now I'm doing is I'm going to try to find the gradient L of beta, which is nothing but del L by del beta S. right? So I'm trying to find the derivative with respect to any component S, and then I'll just stretch that component out and see what that looks like for all components. So taking any component S, if I take its partial derivative, over here, I notice that J is going from 1 to P, and there is only one component in all of these summations that has S in it. All the other summations are essentially constants as a function of S, beta S. And so only the beta sth term will remain, and all the other ones are just zero. So I get the summation I going from 1 to n on the outside, and I just get yi xis, because that's the only term that remains. All the other terms are essentially zero, right? And then over here, I take the derivative, so I get minus, and then summation I going from 1 to n. Then first I have to apply chain rule, so I take the derivative with respect to log, so that becomes 1 plus summation of this, 1 plus e to the power of this summation. Then I have this e to the power, so again I use chain rule. So I have this e to the power summation x, xij beta j, and so I get that. But now I have to take the derivative, according to chain rule, I have to take the derivative of the thing inside the expectation, the exponent. And that is nothing but terms, many terms of beta, but only one of those terms is with respect to beta s. So again, all of those summation terms are zero, except the sth term, in which case I only get xis remaining. Okay, so now there is an xis term here and an xis term here, so I can pull that outside along with this outer summation. So what I get is yi minus this expression, but then what I realize is e to the power a divided by 1 plus e to the power a is actually nothing plus but 1 plus e to the power minus a. Okay, so I use that to just have this minus sign over here, and I get this particular summation. Okay, now this is the partial derivative with respect to S, and every single element looks exactly like this. So the first partial derivative with respect to 1 or beta 1 looks like xi1 times this same number, because there's nothing about S in here. Then xi2 times the same number, which means I can take the vector x and just take that whole vector, multiply it with this constant, and add those vectors up, and that's going to be my full gradient vector. So if I assemble the whole vector, the whole gradient vector is this expression over here. Okay, now if you can't see it in one go, don't worry about it. You can use the element-wise differentiation if that works for you, and that's completely fine. Now we can do it directly as well. So instead of taking, the element-wise derivatives like we've done here, we can do it directly. So when I say we can do it directly, is I can write the gradient. If I want to calculate the gradient, then over here I look at this expression. There's only one beta term here. I'm taking the derivative with respect to beta. So that one term that's only a single polynomial goes away, right? And I just get from here I just get this expression. Okay, then when I solve this, I get this summation xi yi minus this expression, which is again 1 divided by 1 plus e to the power minus xi transpose beta. I'm not really going into this in a lot of detail because this requires matrix differentiation. If you're not familiar with it, then don't worry about it. We've done the element wise, and that's good. But at the end of the day, we get the same gradient. And now remember, we want to optimize this function, and so we set it to 0. Once we set it to 0, we want to see whether an analytical solution is possible in order to solve beta, but it is not. Beta is inside this summation, and there's no way to separate that out to actually get a solution for beta. So an analytical solution here is not possible, and thus a numerical optimization tool is indeed required. But if I'm going to implement Newton's algorithm, I want to be able to know for sure that, the Newton's algorithm will converge. And in order for us to implement Newton's algorithm, I need the Hessian or the second derivative. So that's the next job. So we need to find the Hessian in order to know whether we have a concave function, but we also need to find it too in order to implement Newton-Raphson. So we have the gradient vector over here in this expression. Now this is the partial derivative with respect to any beta s. Now next to it, if I do another partial derivative with respect to any beta, let's say k, and take this partial derivative over here, that's going to give me the k and sth term of the Hessian matrix. Okay? And that's really what I want to focus on. So here's what we do is now let's take the derivative again with respect to beta k. So del square L beta by beta k beta s is del by del beta k of the sth, the partial derivative with respect to beta s, which is something we already had done before. But now the good part is that this is just a constant as a function of beta k, so this goes away, and I only need to look at this term. So the minus comes outside. I just have partial derivative with respect to beta k of this expression here. And now I do exactly what I've done in the previous setup, is I notice that, okay, I do my chain rule, is this expression comes outside. I get 1 plus e to the power this whole squared. Then I look at the constant next to e to the power beta k, and that is nothing but just xik. Again, all the other terms in this go away, become 0. The only expression that's left is the one whose derivative with which we're taking. Right? That's the only expression that's left. So I just get xik. So finally, I get a minus on the outside, summation I going from 1 to n, xik, xis, e to the power this summation divided by 1 plus e to the power this summation whole squared. That's my Hessian matrix. So this basically then corresponds, like I was saying, to the second derivative del squared L, or the kth element, of del beta. The kth element of the Hessian matrix is what this corresponds to. But then again, I can look at exactly what that matrix looks like altogether. That matrix, the Hessian matrix, remember, is denoted by a nabla squared L beta. And then what I notice is that, this is a summation of xik and xis. Now let's ignore this part for now. So what is this? Remember that this is independent. This part doesn't depend on k or s, the two indices with respect to which we've taken the derivative. So this is essentially the same irrespective of, it's basically the same number that's being multiplied to every element of the matrix. Okay. So the question is that, how do I actually look at this? So, so if I have summation xik, xis, I going from 1 to n, well, this actually is nothing but the matrix X transpose X. Why? Well, if I take let's assume my X matrix is a long matrix like this, where it has a large number of rows and a relatively smaller number of columns, which is very typical of logistic regression. Well, then X transpose looks something like this, and X looks something like this. Okay. So if I want to look at the first element of, and this is X transpose X. Okay, so it's a square matrix. If I want to look at the first element of X transpose X, well, it's going to take every element here and every element here and multiply and add them appropriately. That means it's going to take X, it's going to do a summation over all the rows of X over here and the pairwise products, which is nothing but this, all the pairwise products and all the rows. Right? That's basically what this is doing. Okay, but then also we have this term that's getting multiplied to the whole matrix as it is. Right? So it's getting multiplied to every element. So how do we get some number that is multiplied to every element, except that some number is different? It can be a little bit different because it depends on xi, right? So this summation, so what I'm trying to say is that this depends on summation and there is a summation over here as well, right? So it's not that the same number is being multiplied to every element of the matrix, but pairwise or element-wise, the same number is being sort of multiplied along with the summation. So the way to see this is actually that instead of this being just X transpose X, this becomes, so there's a minus over here, so the minus comes down, and you have X transpose X, but along with a W matrix in the middle, where the W matrix is nothing but an n by n diagonal matrix, where the diagonals are nothing but e to the power, just this, e to the power xi transpose beta divided by 1 plus e to the power xi transpose beta squared. So it just becomes, basically, what you end up having is, this matrix times this W matrix, where this W matrix is just a diagonal matrix with zeros, along with this X matrix. Okay, and this is a diagonal matrix, like I was saying. Right? So this becomes your W matrix, and this is your X transpose, and this is your X. And this turns out to be your Hessian nabla squared L beta. Okay, so all I'm trying to do, if in case you're confused, is I have found out what the element-wise expression of the Hessian matrix looks like, but I want the whole matrix formulation of what does it look like in the form of a matrix, because it's going to help me. And this is what it looks like in the form of a matrix, right? So it simplifies quite nicely. But the reason I'm doing this is because I want to check whether my matrix is positive definite or negative definite, sorry. So notice that this Hessian, this is wrong. It's not positive definite, it's negative definite. And the reason I can see that this is negative definite is because of the conditions that I discussed in the previous video. Is, let's say you consider a vector A in Rn. Okay, if I consider a vector A in Rn, I think it should be Rp, not Rn. Oops. Rp, not Rn. And if I multiply A transpose Hessian L beta A, then I know that this will be negative definite if this is guaranteed to be less than 0 or less than equal to 0, right? Well, and I substitute what this looks like back here, so I get a negative outside, A transpose X transpose W X A. But then A transpose X transpose can be written as XA transpose W of XA. But now, what is this? This is basically a squared term. This is a diagonal matrix, right? A diagonal matrix where every element is positive. And these are just products of positive terms. And this is a scalar quantity, which means that this is definitely less than equal to 0, because since the above is a product, since the above product is a sum of all non-negative terms. Okay. Which means if it's a product of all non-negative terms, this part has to be greater than equal to 0, with the negative outside has to be less than equal to 0. Which means that our objective function here is definitely concave, which is great, because it implies that when we implement Newton-Raphson's algorithm, it is in fact guaranteed to converge, right? Because I know my Newton's-Raphson algorithm, when it has a concave objective function, it is guaranteed to converge. Right? It will not diverge, it will not converge to local minima, it will converge to my global maxima. Okay, which means I can now use this to do my implementation. So what does the algorithm look like for this logistic regression problem? I start from an initial guess. Now, in this case, an initial guess is tricky, but because there's no sort of default value except maybe 0. Because I know that if betas are 0, then my probability of success is basically going to be essentially, is basically going to be half. Because if this is 0, then this whole expression becomes 1, this whole expression becomes 1, and so I just have yi's being half, which means with probability half, it's going to be a success. With probability half, it's going to be a failure. Okay, so assuming a decent value of beta is 0 is basically assuming that the covariate xi's have no information that it's giving us about y, right? Because probability half is exactly what a blind guess would look like. So we're trying to we think the x's are useless in explaining the y's, which means betas are 0. That's my first guess. And I'm going to let the Newton-Raphson algorithm prove me wrong and go in a different direction. Okay, so the second thing is you choose some, oops, this is not needed, sorry. I'll try and clean up the notes before I sync them. And then I do the following. So I set up my starting value, and then for iteration k plus 1, beta k plus 1 is equal to beta k. Oof, there's another typo here. This should be minus, not plus, because I know that in my Newton-Raphson update I have a minus. Beta k minus the inverse of the Hessian times the gradient vector, right? And so these are all the values I've already obtained. Okay. Now, what I'll do is I'll check whether the gradient f prime, so here again, this should be not f prime, gradient L beta k, if that is small enough. Okay, I'll clean up the notes when I put them online for you. But when the norm or the size of the gradient vector is smaller than some bound, I'm going to stop and say this is my estimate of the beta regression coefficient in the logistic regression example. Right? Now I know all of these quantities. I know my x, I know my w's, I know my y's, my xi's, and the beta k, the current iterate, I also know. So I can keep going and iterating these things. Okay, so we'll see in the next video, we'll see a coding implementation on a real data set for this as well.